Hello everyone. So I extend very warm welcome to every one of you to the first live interaction session for the Rapid Manufacturing course. This is Falcon Gupta, PMRF scholar and a PhD student in Material Science Department at IIT Kanpur. And I'll be dealing with the interaction sessions for this course. The course instructors for this course are Professor J. Ramkumar and Professor Amandeep Singh, Department of Mechanical Engineering, IIT Kanpur. I hope I'm audible to everyone and my screen is visible. If any one of you could verify. Okay, so during the sessions, we'll first be going through the summary of the lectures to have an overview of what is being taught during the week. And then we'll try to solve some of the questions in the sample problems. Okay, so the sample problems in this course are of theoretical nature of one-word answer types. So we'll basically focus our understanding to the actual concepts. So to begin with, let us understand what is meant by the term rapid manufacturing. So since this is the title of the course as well, we should clearly understand what is the meaning of this term. So what is rapid manufacturing? Nowadays, when we go to the market, we need products that are customized to our requirements. For a very common example is majorly all of us are right-handers, but some of us are left-handed people as well. But all the products that are available in market, they are majorly for right-handed people, and so left-handed people have to suffer. So there comes the part of mass customization. So rapid manufacturing deals how the parts can be customized as per the needs of the customer, as per the satisfaction of the customer, without losing on the integrity, the quality, or the cost of the products. So at the same time, when we are customizing things for the customers, we should keep in mind that its cost should not go high, as the product should always be affordable. And it should have the similar kind of strength characteristics as the bulk products have, or the products when they are manufactured in large batches. So to summarize, rapid manufacturing is actually creating durable and safe products for sale to real customers as per their needs, as per their satisfactions, in moderate to large quantities. So instead of uh, instead of having single catering to the large number of customers in a more generic way, through rapid manufacturing, we now aim to cater to the requirements of the customer in more customer centric way. So now, why rapid manufacturing? Since this is the key buzzword nowadays, why? Because the product life cycle has decreased due to this rapid manufacturing. Due to the advent of the technologies, the product life cycle has decreased. Hence, we require rapid manufacturing technologies. Now, how the product life cycle has decreased? With innovations, we have assembly lines and uh, manufacturing techniques that could manufacture a particular product within a very less time frame. So, for example, as given in the lectures as well, for the four free-form fabrication technologies. which is F3T. Here, they have reduced their manufacturing product time for almost 6 months to few weeks. So, what does this mean now? This means that they can have more advanced or modified products with every few weeks. This would mean that the existing product will go out of market very soon. Earlier, it was going out of market in 6 months, but now it would go out in somewhat few weeks. So product life cycle has decreased. So that is why we require rapid manufacturing so that these timelines could be met easily. Now, we see, but manufacturing products as for individual customers would incur high costs. All right. So these high costs means that it won't be affordable anymore. But our motto is not to make the products unaffordable, but to make them affordable and as per needs. So we see when we deploy few products, so when we have fewer number of products in each cycling, so as we see we have fewer units, we have lesser manufacturing costs for additively manufactured products. But as we move towards more units, conventional manufacturing techniques have lower cost. But using conventional manufacturing techniques, we cannot cater to individual requirements. And as we are catering to individual requirements, our batch sizes has also reduced. Batch sizes has also reduced in catering to the individual requirements of the customers. So here comes the role of additive manufacturing or rapid manufacturing. So what is currently the status of rapid manufacturing right now? So we have additive manufacturing as the technology which is used to achieve rapid prototyping and rapid manufacturing. These are basically the application parts of this particular additive manufacturing technology. So this is one of the buzzwords nowadays and a key technology that is being researched all around the globe. Now their application paths comes rapid prototyping and rapid manufacturing. So as the term prototyping suggests, rapid prototyping deals with the making of prototypes, that is, their scaled parts to check the feasibility of the final part, whereas rapid manufacturing is used to develop the final product. The functional final product, rather, I should say. Now, in rapid prototyping as well, we can have prototyping in multiple ways. One is solid imaging and concept modeling. The other is functional prototype, then prototyping tools. These are key things in rapid prototyping. And then in rapid manufacturing, we have direct tooling and direct manufacturing. Then, as a part of rapid manufacturing only, we have indirect prototyping, indirect tooling, and indirect manufacturing. So, these are all towards the left, these are the direct processes based on additive manufacturing. But towards towards the right, these are indirect processes. And to make a note, these are not based on additive manufacturing. That is the final product that is coming out of it is not additively manufactured. All right. The final product that is coming out of these techniques is not additively manufactured. Whereas in these processes, the final product that is coming out of it is directly manufactured. Yeah, just a minute. Okay. Okay. So the direct processes, they are based on additive manufacturing. That is, the final part coming out of these shall be additively manufactured. So now let us look at them and understand them one by one. So what is additive manufacturing? Additive manufacturing is a layer by process, layer by layer process of addition of material to fabricate the final part. Okay. So this is a layer by layer process of addition of material. As the name suggests, additive manufacturing, it means the addition of material. So material is added in a layer by layer manner to fabricate a final part. Now suppose you have to build a cube. Now what an AM machine will do, first it will discretize this cube into multiple layers of uniform layer thickness. So we work with uniform layer thickness in additive manufacturing. So suppose it is discretized in this way. So these are the multiple layers in which this cube is discretized and they have constant uniform thickness. Now what the machine will do, it will start building the cube in a layer wise manner. Suppose the material is deposited in the first layer. Then as it solidifies, the material is deposited in the second layer and time is allowed such that it solidifies and then material is added in the third layer. This way, subsequent addition takes place in a layer-wise manner to build the entire cube. So you can use this to build more complex shapes like lattice structures or conformal cooling channels, heat exchangers, internal cooling channels, etc. Now, what is the workflow to successfully additively manufacture a part? So there are certain steps involved in additive manufacturing. So the first step is the generation of the data set for the CAD model. So this you can do using any softwares that are available with you. Some of them can be SolidWorks or AutoCAD or Fusion 360, any software that you are comfortable with, you can work with those and develop a 3D CAD model. CAD model is computer aided design. Now, once you have this CAD model, you need to convert this into STL format. STL stands for Stereolithography or Standard Tessellation Language. Okay, so what happens in this is, when you convert your CAD model to an STL, it stores the surface information. So what it will do is discretize it will discretize your CAD model into a number of triangles, suppose a cube. So it will tend to discretize the cube into a number of triangles, the faces. So this is the discretization of a cube. It has divided the surface into triangles. Okay, so it works on the principle of minimum number of polygons. Okay, now when you have added this when you have converted this into an STL format, now what you need to do is you need to develop machine readable G codes. So the machine cannot directly read your STL file, you need to slice it as what, that is, you need to tell what constant layer thickness should be maintained. Taking the example of the cube only, you need to tell what thickness should that be cube sliced at. Say suppose this is 10 mm, so should it be sliced at 1 mm or 0.5 mm or 2 mm. So higher the thickness of the layer, higher will be the surface roughness. Okay. So to understand this concept, then we need certain softwares that will automatically do this slicing. Okay. So we are going through these so that we could actually solve the sample problems, because this is necessary to understand the concepts. So once you have converted those into machine readable G codes, you feed them to the machine and it actually goes on to 3D print. Once you have 3D printed, you have your actual 3D printed component with you. Then you remove the part from the printer and post-process it. As per your requirements. So the requirements can be during these processes, there is certain level of surface roughness that is induced on the body. So you can either finish it using other machining techniques. Okay, and there are certain level of residual stresses present as well. So they can be treated using some heat treatments, etc. Okay, so this was the workflow of additive manufacturing process. Now, one of the examples of the process is stereolithography. This is one of the earliest process that was developed for additive manufacturing. So what this process use is a UV curable photopolymeric resin. It uses UV curable photopolymeric resin. Okay. So what is UV curable photopolymeric resin? This is a resin which actually responds to UV light. As soon as a UV light is imparted to it, it tends to solidify. The UV light initiates polymerization process, and the resin polymerizes and gives you a solid part. So there is a laser which ejects out a beam which goes through the optics. This optics is lenses and mirrors. It has lenses and mirrors. They help in focusing this beam onto the polymer in the tank. So these are driven through galvanometers. You cannot drive them manually. They are driven through galvanometers. Okay. And you can control only the X and Y motion of the beam through this mirroring system. So, and that is controlled as per the CAD file or the contour information that you have given. Now, suppose if you have a frustum-like shape, so when it starts to, and it has sliced it in multiple layers. Suppose this is 20 mm and this is 10 mm. So this CAD file would guide this optics and mirrors to cover an area of 10 and 20 mm in respective layers on this polymer. So as a single layer solidifies, what this elevator and platform, this elevator, it lifts up this build platform, lowers down this build platform, and a recoater blade applies another layer of this polymer. So you have a new layer of polymer as every previous layer solidifies. And this new layer is then exposed to the UV light. And that UV light now solidifies this new polymer. So what is additive manufacturing? It is a layer by layer process. We have seen the workflow of additive manufacturing. It has generation of data set or the CAD model. Then we need to convert that into STL. Then that should be sliced using certain softwares or into machine readable G codes, as the machine directly cannot read the CAD file or the STL file. So certain softwares are available like the Prusa Slicer or Ultimaker. They are free to use softwares, or Slice CR. These are some softwares that are available which you could use directly. So during these G code generation, you could also control the amount of cooling or the fan speeds or the layer exposure times to the lasers or the travel speeds of the laser, etc. So these are some of the parameters that you can control during this G code generation process. Then you 3D print it, and then you finally remove the part, post process it, and use the part as per your requirements. Now, to take an example of one of the additively manufactured process, we have stereolithography, which uses UV curable photopolymeric resin that uses a laser to eject out a beam, UV beam. Then we have the optics that focuses the beam. Then we have the galvanometers and mirrors that uh, actually controls where the beam needs to project on the resin. And then we have a platform and an elevator system which ensures that the platform is lowered with every layer solidifying. Okay, so this way we have our 3D printed parts. Now, So this was the additively manufacturing technique. So this is technology. Now let us look at the application parts of this technology. Firstly, we'll go to the direct processes and the rapid prototyping. So what is meant by the term prototyping? As I said, it is making the part at a smaller scale just to test out its feasibility. If that part has the accurate dimensions, or is it visually appealing or fine or not, or if its parts are actually functioning or not. So it has three subtypes. First is solid imaging and concept modeling. Solid imaging and concept modeling is in that we just check the fit and the dimensions. So in this, we just check the dimensions only, dimensions and appearance of the parts that we are creating. Okay. So to see if what dimensions we have selected in our design are actually working or not. Say for example, parts of a combustion engine. So if we want to create the gear assembly, so if the gears are meshing properly or not, we can check using solid imaging. Or if you want to see how the terrain is of a particular part, so where you have to make a particular contour, suppose you have to make some contours like this, corrugated panels. So you can have a solid model for this and then check if you are getting proper contours or not. Next come is functional prototyping. In functional prototyping, we check if the part is actually performing one or the other functions or not. In functional prototyping, we check if the parts are performing their required function or not. Okay. So for example, the shock absorbers, we can 3D print them using tough ABS. ABS is one of the FDM materials that has good strength. We can have them printed as functional parts and check if they are like behaving in a similar manner as a final part is expected to. Okay. So it is not necessary that all the functions are checked. So we make individual prototypes for checking individual functions as well. So we have individual prototypes to check different functions. And then they are clubbed together to have a final functioning prototype. Now, the other example is the air vents of the car. So we can see if, suppose that is a 3D printed air vent, and we can see if the slider that is there on these air vents, it is giving proper swing to these air vents or not. Like if they are going through the similar angular range during their swing or not, as they are expected in an actual car. Okay, then we have rapid manufacturing as the application part. So once we are done with the prototypes, we now go on to develop final functional parts that are to be deployed to actual field. So we term that as rapid manufacturing. So it has two sub applications, that is direct tooling and direct manufacturing. So in direct manufacturing, we actually directly manufacture the final part. So for example, dental bridges. or these medical implants, they are very common examples of direct manufacturing because they have highly contoured surfaces. These medical implants have highly contoured surfaces. So these are difficult to be manufactured using conventional techniques. So then there comes the part of additive manufacturing. So as you can see, human teeth, they are highly contoured. So they are made using direct manufacturing. Whenever you build a product directly out of this, then it is called direct manufacturing. So these dental bridges, say these tooth of very contoured shapes, they are made using additive manufacturing. The crowns that people use, they can be made using this. So using some biocompatible metals or biocompatible materials, this is possible nowadays. Now comes direct tooling. So one is we build directly the part. The other is we build the molds and insert using additive manufacturing and then build the final part using these molds and inserts. For example, for conformal cooling channels or balls, they cannot be directly made, but we could surely make molds and inserts for them to make uh, these final parts. So, for example, for a golf ball, so as we see, the golf ball has dimples on it. So, to have a better and a faster production for that, we can have a mold that is 3D printed having these impressions on its surface. So we have this mold that has these kind of impressions so that you can have the final golf ball when you cast it using this. So direct tooling refers to the process of making molds and inserts. Now, one of the type is prototype tooling. Okay. So prototype tooling is, as if the name suggests, that it is for prototyping. So when there are very quick changes made to the molds, so in such a case, we could make molds of materials that would sustain a little less than stronger molds, since there are changes to the molds very fast. So in such a case, we use prototype tooling. So we make molds using materials that function as actual molds only, but they have lesser strength. So, for example, shoe soles. So, for having shoes pertaining to the requirements of every person. Say sometimes what happens is when we go to the market, we need to buy a shoe. So there are numbers in integers like 8 or 9, but I want 8.5 middle in the middle range because 8 is too tight or 9 is too loose. So in such a case, when we need to cater to requirements of individual customers, this was require a quite large number of molds. So that time prototype tooling comes into play. Now, when we combine the effects of prototype tooling and direct tooling, it comes under rapid tooling. This is rapid tooling. Now, these were the direct processes. Now, indirect processes are where the final product is not additively manufactured. So we have indirect tooling, indirect prototyping, and indirect manufacturing. So in indirect manufacturing, what we have is we make a 3D printed part, say suppose engine, a full scale size engine. So we make using some polymer, 3D print it using some polymer, then make a mold out of it, and then use this mold to make engines of actual metal, of say aluminium. So then this is indirect manufacturing, where this additive manufacturing was used to make the parts that was similar in shape and size or in geometry, and that part was made using a polymer, and it was used to prepare the mold. And now this mold is used to make the engines finally. Similarly, we have indirect tooling. So for indirect tooling, for loose wax casting patterns, where the wax is ultimately lost, what is done is the pattern is made using AM. Then you develop a mold out of it. Then you develop molds out of it, and then you make a mold. Then you develop some parts that are rigid, and ultimately make other molds of different material, because AM has material restrictions. You cannot use all and every kind of materials in additive manufacturing. So we need to play with that. And similarly, we have indirect prototyping. When we directly do not make prototypes using additive manufacturing, but suppose we need to have a flexible silicon body. Then what we'll do is we'll make a rigid part out of additive manufacturing then make a mold out of it, and then we'll do a silicon casting in that mold to have ultimately flexible prototype. So that is indirect prototyping, because we are directly not getting the prototype. So now this was the summary of the lectures that were delivered during week 1. So now let us go to some of the sample problems and solve them one by one. So the very first question is, the use of additive manufacturing is increasing continuously, which makes it competitive with other conventional manufacturing processes. So here, conventional manufacturing processes are the existing processes such as lathe or milling, drilling, or all the kind of subtractive technologies. So additive manufacturing is increasing continuously. Yes, it is increasing because of its capability of making complex geometries which could not be achieved using these conventional techniques. And because of its capabilities of catering to customer centric requirements, okay, and because of its capability to produce colors in material, or that is we say functionally graded materials, so we can tune the printing cycle in such a way that we have variation of properties along the length of the body. So suppose this is your 3D printed cuboid, so we can just impart certain printing parameters such that it has a variation in properties along this direction or any along Z direction, along the print direction or any of the other directions as well. The next question, the manufacturing process which adds material from all spatial directions by jetting discrete volumes on the emerging object is known as additive manufacturing, ballistic particle manufacturing, subtractive manufacturing, or none of these. So we know additive manufacturing is a layer by layer uh, building process. So if we closely look at the process, we see that the material addition is only in one direction. So when you build it in a layer wise fashion, suppose this Z direction, so we see addition of material is only in one direction. That is the Z direction. So it is not adding material from all the directions. So this is not our answer. No addition of material from X or Y direction. Now, next is, now let us look at subtractive manufacturing. So in this, there is no addition of material. In subtractive manufacturing, there is only removal of material to make the final part. Okay, so this is also not our answer. Now comes the ballistic particle manufacturing. So what happens in ballistic particle manufacturing is for building of a particular object, discrete particles or very fine particles, they are exploded from all the directions. From all the directions in three-dimensional space. So suppose you have this object of yours, say some shape, and your particles are being deposited onto this from literally all the directions. Okay, so in this we can say that material is added to the body from all the direction. It then settles down on this and the part is formed. So we have ballistic particle manufacturing as the answer. Now we can obtain, third question, we can obtain the data set in engineering by 3D CAD design or computerized tomography scanning. True or false? So 3D CAD design, as told earlier, is three-dimensional computer aided design. So herein you use com- uh, computers and softwares to develop your own designs. Now, when you develop your own designs, what you impart as an information, you impart X, Y, and Z information actually. So you say you provide data set. You provide data set of X, Y, and Z coordinates. So simplest example, you are giving a cube. So you are giving the information that suppose this is the origin. So this is 0, 0, 0. Now this is X, Y, and Z supposedly. So this is say 1, 0, 0. This will be 0, 1, 0. And this will be 0, 0, 1. Correspondingly other point. So you say the material is, or the object lies within these coordinate ranges, so that when your tool moves, it moves in these range only. So we can obtain data set using CAD designs. Now, computer tomography scanning. So in very common language, this is what is termed as CT scans. So there are certain devices which go on to scan a 3D object and then gives you the information about the contours or the surface morphologies. Okay. So when it gives us information about these, so it actually develops a data set pertaining to X, Y, and Z coordinates again. So we say, yes, we can obtain data set by using 3D CAD design or computerized tomography scanning. So moving on to the next question. Generally, additive manufacturing is a what dimensional process? So we have options as 1D, 2D, 3D, and 2.5D. So 1D, 2D, and 3D, they are the common terms. So 1D is when you can, is when you have access only to one of the three dimensions. Only one dimensions is accessible. Okay. Out of the three X, Y, and Z, you can access only one, that is either X or Y or Z. In 2D, now you have access to two of the three dimensions. So two. So you have in combinations of XY or YZ or XZ. These are the combinations that you can have. And in 3D, you have full access to the entire space. Okay, so that means you can travel along all the three axes in the entire coordinate system. Now, what is this 2.5D? So we say in 2.5D, you have access to two full dimensions and one half dimension. And the third, you have only half dimension access. So what does it mean? So additive manufacturing is actually a 2.5D process and not a 3D process. Why? Because there you can traverse any length across X and Y. So this is the printer bed, suppose. So you can go any length along X or Y. But along Z, you can move only in steps of constant layer thickness. So since we have limited access to the Z direction, we have limited access. We say it is a 2.5D process. Had we been having full access to the Z axis, it would have been a three-dimensional process, but we cannot go to any layer thickness anytime. So it is like if I have selected a layer thickness of 1 mm, then I need to travel in steps of 1 mm only. It cannot be like I travel 2 mm here, then 1 mm here, then 3 mm here. No, it cannot be done. So it is a 2.5D process. So next question is, additive manufacturing does not interfere with the design process. True or false? So this is true. This is the main advantage of the additive manufacturing process. It do not pose any kind of restrictions pertaining to the designs that we could process through it. So we have literally no restrictions pertaining to the designs that would be processed through additive manufacturing. So we can clearly say that it never interferes with the design process. Now, next question is, only one type of additive manufacturing process can be used to solve a problem. True or false? So we have, firstly, we have multiple types of AM processes, which we shall be covering in the later lectures. But to give a brief overview, we have FDM type, that is fused deposition modeling, wherein a polymeric filament is extruded through a nozzle in a molten state, and it is then deposited on the printer bed to develop the 3D part. Then we have selective laser sintering, which is SLS. We have selective laser melting. So in these two processes, SLM, in these two processes, laser is used either to sinter the powder particles or to melt them. So one process is using sintering, other uses melting. Next is electron beam melting. So this is also one of the AM processes which uses electron beam to melt the powder particles. Then we have, as we saw, stereolithography, which uses lasers and UV curable photoresins. Then we also stereolithography. Then we have directing writing, where a liquid slurry is extruded through a nozzle and solidified in generic air atmosphere that is available. Then we have laminated object manufacturing and so on. The list is long. We have many more technologies, AM techniques, sorry. Okay, so it is not so that if a problem can be solved using one, it cannot be solved using other. So these can be used always interchangeably. We can what design we can use, make using SLS, we can use make using SLM as well, using EBM as well, using stereolithography as well. So it is not so that only one type of additive manufacturing can be used to solve a problem. The next question is, additive manufactured entity is called a dash if it shows all characteristics and functions that are allocated to it during the product development process. Assembled or disassembled part, product or prototype, balanced or imbalanced part, or none of these. So the entity is showing all characteristics and functions. So whenever the object displays its function, it is said to be either the product, or if it is a scaled version of it, or uh, some scaled down or scaled up version of it, then it is called a prototype. So the answer is product or prototype, as it is showing all the characteristics. All characteristics includes geometrical features and contours, as well as the functions that it needs to exhibit. Here the functions means that is the loads that it can bear, the motions that it needs to make, for example, if it needs to have certain rotation from say 0 to 90 degrees, okay, or say it has to have some translatory motion. So it should, if it is exhibiting all those, then it is either a product or a prototype. Now, rapid tooling involves additive manufacturing procedures that leads to parts. These parts are used as cores, cavities, or inserts for tools, but not as dies and molds. So, true or false? What does the term rapid tooling means? During tooling, you mean everything including dies, molds, cavities, pores, or inserts. Since molds and dies are also one of the tools that are used to fabricate a final part. So, saying that the parts developed using rapid tooling cannot act as dies or molds, this is false. All the parts that are developed using rapid tooling, they can act as dies, molds, cores, cavities, inserts, everything. So the next question is, the productivity of a plastic injection molding can be dashed by increasing the heat extraction. So what is plastic injection molding? In plastic injection molding, liquid polymer or molten polymer is pressurized to enter into the mold cavities, where they solidify to form the final required part. So, as the solidification speed enhances, its productivity can be increased. And how to increase this solidification speed? By increasing the rate of heat extraction. Higher the amount of heat extracted, the faster it would solidify. And the faster it would solidify means that the machine would be ready to have another round of production. So the productivity can be increased using heat in by increasing the heat extraction in plastic injection molding. Now, rapid manufacturing cannot be used to make safe and durable products. So this was in the definition itself. So it is used to make safe and durable products for sale to the real customers. So this term is false. If the products are neither safe nor durable, then the whole point of rapid manufacturing collapses. So then there is no point of having rapid manufacturing. This is false. The products are safe and durable as well. Okay. So these were some of the sample problems uh, in this for week 1 lectures. So today we discussed what actually is rapid manufacturing and why is it becoming important nowadays because of the reduction in product life cycle and meeting to the requirements of customers in a more specific way rather than a generalized or an average way. We need rapid manufacturing. Then we talked about the status of the rapid manufacturing techniques and how they are being implemented at the prototyping and the tooling and the manufacturing level. We saw additive manufacturing in detail with its definition and the workflow and one of the techniques. And then we had examples of different applications. And then we discussed certain questions, sample problems for this additive manufacturing techniques. So in case you have any doubts, you can always post them on the discussion forum. We can always take them in these meetings. And also you can ask the questions during these interaction sessions as well. So if anyone has any questions. Okay, so if not now, you can always post them on the discussion forum. And these video lectures and PPTs shall be provided through you through YouTube links and Google Drive links. So I'll close this session and let's catch up in the next session next week. Thank you, everyone.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thanks a lot, everyone.